Hello, hello. So, ladies and gentlemen, and all of you in between, please take your seats. We are starting our afternoon section with Andor Menczer, who will continue Legezer's talk about his Tensor network algorithms.
Hi, everyone. My name is Andor Menczer. I'm a PhD student at Eötvös Loránd University. I'm also a junior research fellow at Wigner. And I'm in the same research group as Őrs Legeza, who is also my supervisor and the head of the research group. He just gave you a presentation before the lunch break. So this is sort of a continuation of that presentation. And because that worked like a minute ago. And now it works. Okay. All right, so you are already familiar with the tensor networks and the DMRG, which, by the way, stands for density matrix renormalization group, which is a subset or a subgroup of tensor network algorithms. So I will just skip the introduction part and jump straight into the middle. What matters is that in very simplified terms, physicists are mostly interested in is the math related to quantum mechanics, which if we were to simplify things a little bit, it works as follows. An input model goes in, the magic, the quantum simulation happens, and what goes out is not the exact result, but linear algebra. That is, we have structures within structures within structures, and if you go down, eventually you will find familiar faces in the form of vectors and matrices. And alongside the data, we also have oh, sorry. Okay. Yes. All right. So sorry, I wasn't paying attention. All right. So what happens is that we have the data, which are like vector and matrix like operators, but they can be somewhat convoluted. What matters is that we also have description tables. They are the ones telling us how these structures are related and what kind of operations we need to execute in order to get the exact result, which, by the way, is not the final result. We feed this we feed the output back into the system, and it goes on and on and on for a lot of iterations. And this is important because we could just one by one loop through the operations, do the calculations, and we would get the result. And it would work technically. However, it would be very slow. We are not interested in simulations that take, for example, half a year. We wanted to run overnight. So for that to work, we take this intermediate result, which boils down to it's a lot of data, a lot of number crunching, and we feed this into another system, which is no longer about quantum physics. It's more about scalability and number crunching and matrix operations. So this is no longer a physics problem. This is more like a computer science problem, and this is about basically marrying the physics model with the actual hardware. And this is how I come into the picture. I'm a programmer, not a physicist. And if life was simple, we could just take an accelerator GPU, for example, copy the data into GPU memory, run the calculations, and then copy back the results. However, even if we had infinite performance, which we don't, but even if we did, it would be very sluggish because just the copy operations themselves would be very, very slow. And one could argue, why don't we use unified memory? We should use the right hardware for the right job, after all. However, eventually, if we scale the system, we will run into this problem. For example, if we have 8 GPUs and a lot of CPU cores and unified memory, we might not have memory I/O related slowdowns internally. However, with a little abstraction, I could say that this whole system with multiple GPUs is essentially just a super GPU. And if we take multiple of these super GPUs, then we end up with the same problem. We have multiple devices, each with their own memory. And in order to get proper high performance, by the time we start the calculation on each of these devices, the data has to be preloaded and available locally. So what generally people do in such cases is that we try to group the data into sets of data where inside each data set, data locality is high, which means that calculations that are near each other will use data that are also near each other, and hopefully the same set of data. So we can load these sets of data one time, run a lot of calculations related to that particular set of data, and then move to the next one. And this would work if we were, for example, sorting candies based on our colors. However, these structures can be very complex and related to each other in multiple ways. So we can't just create completely different groups. There will be a lot of overlaps. For example, if this graph could talk, then A could be, and I can also point, yes. So if this image could talk, then maybe A would call itself vehicles in general, and then AB, which is a subset, it contains A, so it's also vehicle, but it contains additional specific information. For example, it would be cars, and then this one, the green leaf node, could be electric cars. The other one, internal combustion engines, cars with internal combustion engines. And we could treat the whole group as one, but that maybe would be too large and wouldn't fit into memory. So we have to cut into smaller and smaller groups. However, that means there will be eventually some kind of overlap. So what we do is we can create a tree-like structure based on the dependencies and how overlapping data is related. And the way the execution goes is from left to right on the leaf nodes. And in the background, the way we load and download memory is effectively just a depth first search. So we can load the data related to cars, and then load data related to vehicles, and then extra information specific to cars, and then specific to electric engines. And when we move from the computation perspective from one leaf node to the next one, what happens in the background is that we can delete D, which in my example is electric engines, and move back to this one, and then we can move to the next leaf by loading E, which in my example was internal combustion engines, for example. So this way we can create groups as small as we want. There will be overlaps, but we can still exploit the fact that these are very similar groups. So if we traverse the graph in such a way that will give us much better or more optimal performance. And also this traversal is very efficient in terms of buffering, because we can just instead of constant allocations and deallocations, we can just allocate the available memory on the GPU when we start the algorithm, and then it works like a cassette, like recording on a cassette. So we go from left to right, and when we go up the tree, essentially we just rewind and then start overwriting. So there's no deallocation, no allocation, just using the same buffer from left to right. So it's sequential reads and writes, which is very fast. So this is the basic concept. So to reduce the I/O part enough, so the main bottleneck becomes the computation. The next problem we encountered was that by default, the way the kernels we launch on the GPU devices, their size, how many kernels we have, etc. So the characteristics of these kernels is based on the type of C and not on the type of hardware we have. So to get the best performance, we should there should be a synchron. Sorry, the GPU devices and the way they are built and the way the kernels, the characteristics of each kernel is, there should be a sync between these, and that means that we need tools to somewhat control even strided batch matrix multiplications, which is essentially the same, but we just use offsets. So it is somewhat less of an overhead. This is nothing new. This is industry standard. However, the problem with just using straight up strided batch matrix multiplications is that if we run multiple matrix multiplications, we end up with multiple results, and that gives us an extra step at the end. For example, if we have an operation that has summation, then we need to do another additional step, which is usually called sum reduction. So we have a lot of outputs, and we have to merge them into one, reduce the many outputs into one output, and that is an additional step that we would not require if we were not parallelizing this step and just running them sequentially, which is very slow. But this means that the overhead of parallelization in this case would mean additional calculations and maybe additional I/O operations, which we do not want. So what we did is that with a little pointer trickery, we can use the same matrix functions that we have used previously. For example, the vendor provided a generic matrix multiplication function, so we don't need to roll our own kernels, which might be slower, or even if we spend a lot of time fine-tuning them. The problem with rolling own kernels is that when a new hardware is available, the vendor usually provides updated libraries for that specific hardware. And if you have your own kernels, then you have to constantly update them all the time, every time something new comes out. And that is just from a programming perspective, not a very viable option. However, we can still use the same vector and matrix operations, just with a little trickery of pointers, offsets, and stride values. What we can do is, instead of placing matrices next to each other, the output matrices of a batch matrix multiplication operation, that's how usually it goes, and each row is just a vector of each matrix in this picture. And what we can do is, instead putting matrices next to each other, we can interleave the vectors of matrices, and that way we end up with vectors of different matrices, but with the same index, and these will be the vectors next to each other. And since they are sitting sequentially in memory, we can reinterpret these without any actual data movement into one giant long vector. So if we have, for example, these multiple output vectors from multiple output matrices, then we can reinterpret them as a singular long vector. And if we concatenate every single of these long vectors, we end up with a very huge matrix, a stripe-like matrix. And depending on how we played with the offsets, the pointers, and stride values, we either end up with a vertical or a horizontal stripe-like matrix. And this requires no additional step. This is just pointer trickery, pointer arithmetics. And this is great because we end up with, on the left-hand side, a very large horizontal stripe-like matrix and a very long vertical stripe-like matrix on the right. And when we do the last matrix multiplications, we just apply generic matrix multiplications. And the function doing the matrix multiplication doesn't have to know that these are not actually not one matrix, but this is actually a strided batch matrix multiplication with a little cheat. And since matrix multiplication has a built-in sum reduction, essentially, we will end up with a single, with just one output matrix, which is great because that means we could vectorize our matrix operations without increasing the number of elemental calculations we need to do. And also it has no IO overhead compared to standard operations or standard computation. And as I said, we can use normal already existing libraries, so we don't have to write our own, which is also great. And this is a runtime grouping. So that means if I want to have a lot of smaller kernels, because that's how the hardware gets good performance, then I can do that. For example, if I have 1,000 small matrices, same size small matrices, or matrix pairs, essentially, because I want to multiply them. What happens is that I can just leave them be and do 1,000 kernels. I can combine every 10 of them into 100 kernels. I can combine all of them into a huge kernel and just run one single kernel on the GPU. So depending on the hardware, I can group in many ways, and I'm pretty sure that finding the optimal one is pretty trivial for every supercomputer we want to run this simulation on. And this is great because this means that we are no longer bound by the input, and we can we have complete control in runtime over the number of kernels and how heavy each kernel is, which is great. And the other part is that in many cases we want the GPU or the accelerator to handle the heavy lifting, which usually includes bigger kernel is better as long as we can fit the data into memory. However, there might be a lot of tiny calculations inside these description tables, or the description tables might tell us that we also need to do hundreds of thousands or even millions of very tiny computations. And in a lot of cases, it's just no matter what kind of trickery we try, it's just not worth to run those on GPUs. So in those cases, we can run those simultaneously on the CPU. So we end up with many CPU cores and multiple GPUs at the same time. Oh, and the part I missed is that so we can, if we have a big tree-like structure, we can break it down into smaller subtrees, and then we can run each subtree essentially on different GPUs. So once we have this model, then running on multiple GPUs is pretty trivial. Okay, so yes, the other part, which is the CPU. Oh, okay, that's not much. Okay, so sorry, I speak a little slowly. Okay, so what matters is that we can on the CPU we want low latency, so the threads shouldn't stop and talk to each other a lot. We can imagine this as like in sports. For example, professional players playing football, they don't have the time to just stop playing and have a little chit chat during play. They are all of them are taking decisions autonomously, and yet they have very good teamwork. And the reason is that because they train together and they have heuristics and pre-imprinted algorithms that help them make the decision alone. But these decisions just happen to be in a way that they end up with very good teamwork. So we have no inter-thread communications. Instead, during compile, we imprint heuristics into each thread, and then each thread is self-scheduled. We end up with very low overhead and very low latency, so we can crunch millions of very tiny operations on the CPU very fast. And I will just skip this. We have very good performance on a single computer, about more than 100 teraflops. But I think my supervisor already showed you this picture. So for the closing idea is that for a single computer, we have multiple papers and the results are very promising. And the next step, and essentially the last step to complete the picture, would be to make the jump from one computer to multiple computers. And this is very similar to this picture where we introduced multiple GPUs, since that is almost the same situation. We need to move data to different devices, and each device has their own memory. So multiple computers are in a lot of ways similar to that one. The only difference, and this is the final thought, is that with GPUs, usually we can saturate the entire bus or all the lanes of all the GPUs from the same CPU. And with massive systems, that's not how it works most of the time. Most of the time, for example, we have 200 gigabits InfiniBand from one computer, but the entire system with all the switches has a total capacity of multiple terabits. So to saturate the system and get all the performance related to IO operations, we need to scatter the data to all the nodes, and then all the nodes start to communicate with all the other nodes, and all of them are receiving and sending at the same time. So it's a bit more complicated. That's still in work in progress. But I think the next paper about this last step, which is multi-node simulations, it will be probably ready in a few months. So sorry about surpassing the time limit a little bit, and thank you for your attention.
There is time for a few questions.
Sorry, I might be a bit confused. Is this T cache, is that on the host memory or it's GPU memory management?
Oh, GPU. So I think that was this side. Yes.
Okay, so that's on the GPU, and
yes. Usually, when the core part, which involves the actual simulation, the actual math, and related to quantum physics, that system outputs a lot of data, and that data resides in RAM. So that's host side, CPU side. So when we run locally on the same computer and on CPU, we can directly access the output. So no I/O operations. We need I/O operations when, for example, this TT cache, which is just the three. The full name would be the tree traversal cache, using data dependency trees, and that's what we talked about. So this is one possibility, and the other one is we are running on CPU, but not on the same computer as the one that did the quantum simulation. So obviously we need Ethernet or InfiniBand or some kind of network traffic to move from one computer to another, and TT cache is basically moving data internally within the same computer, for example, from RAM to VRAM.
Okay, the other, can I have another? Okay. Can you switch to the slide where you had the contractors? You talked about
yes,
low latency threads.
Yes.
Yeah, ultra lightweight. Are these threads, or somewhere you mentioned millions of threads? So I was just wondering.
No. We have the same number of threads as physical cores in the system. So every thread is pinned to a physical core.
But GPU core or
CPU? Sorry,
CPU
the CPU core.
Okay.
And they chew through millions of tasks.
Okay. So it's not millions threads, but tasks. Okay, thank you.
Yes, the number of threads depend on the hardware, but usually we have a few hundred on a server computer.
Maybe for one last question, anyone? And let's move on to the next talk.